Hello, and thank you for watching my presentation today. My name is Kevin Knopp, and I will be talking about the development of stick and detect wireless sensor nodes for fatigue crack detection. To begin, I want to talk about what is a stick and detect wireless sensor nodes. These are wireless sensor nodes that are simply stick to a target structure and start detecting fatigue cracks in that specified structure. Many civil and mechanical structures are susceptible to detraction and damage. Proper non-destructive testing and structural health monitoring measures a subsequent corrective and preventable actions are used to detect these cracks. Fatigue crack is estimated as the major flaw responsible for up to 90% of failures of an in-service metallic structures. The detection of fatigue cracks before structural failure can be found by using these stick and detect sensor nodes. These can save lives, and later on in this presentation we will see how real-world test applications can be benefited from these sensors. The detection of fatigue cracks in early stages of life can be measured using ultrasonic techniques. The other approach is nonlinear ultrasonic modulation, which is based on nonlinear wave mixing in the structure. The manifestations of the nonlinear response appear as distortion and accompanying wave harmonics, and its sum and difference frequency generations are known as sidebands. It's been reported that nonlinear techniques are robust to harmless factors like complicated geometry or moderate environmental vibrations. So moving on to data acquisition, this is conventional wired systems are bulking. These are difficult to apply for inaccessible areas and demand excessive amounts of wires to monitor large-scale structures. This is why it's actually better to have these stick and detect methods. So for the development of these new wireless sensor node, the primary goals are going to be the following: autonomous operation and sensor node with low power working strategy. Microcrack can be detected using this nonlinear ultrasonic modulation technique. No history or data is required for the structural damage diagnosis. Ease to extend to large-scale structural monitoring via wireless networking. And finally, the wireless sensor node is validated on a field bridge. So to begin with the background, we're going to talk about active stick detect wireless sensor development. This was envisioned that once users stick the sensor node to the target structure, that the sensor node will automatically form a wireless network and detect onset of fatigue crack. So basically, once this sensor is connected to the structure, it will give wireless information to the user on a different domain. The sensor node is composed of four major modules. This is being the excitation sensing module, the data acquisition and processing module, the wireless communications module, and the power supply module. The PZTs is chosen because these can easily be mounted to the surface of a target structure, because many of these structures are going to have different types of materials, so they want to make sure that these sensors will be able to apply flat and adjacent to these structures. Development of individual hardware components are packaged in a PZTs consist of three identical circular PZTs manufactured by APC International. And they are packaged by Kapton tape with printed circuit and three SMA connectors. The images to the right and on the next slide are going to be a part of this discussion. The excitation channel consists of several 12-bit digital to analog converters, a direct DC remover and a resistance capacitance, low pass filter, and power amplifier. These are going to be used on these wireless sensors, and this is how these ultrasonic waves are going to be monitored so that the sensor can detect fatigue cracks. Data acquisition and processing modules are chosen as the data logger for these data acquisitions. Again, these are because of the uniqueness of this program setup. The FPGA is implemented with the parallel commutation, and a microcontroller 32-bit ARM Cortex MCU in this module is used for signal processing with developed crack detection algorithms. These algorithms are going to be the main focus to how these fatigue cracks are going to be detected and then alert the user domain that this structure is failing predeterminedly. As stated on the previous slide, these are the background and diagrams for the excitation channel that consist of these 12-bit digital to analog converters and our direct DC remover. They also show a resistance, capacitance, and low filter and power amplifier. These are basically the schematics to how these sensors are going to be used and alert the users. The development of embedded autonomous crack detection algorithms are shown on the right. They are also using these formulas for skewness and median. The nonlinear ultrasonic modulation technique and binding condition and autonomous crack detection algorithm is developed and embedded into the sensor node. This is going to be the algorithm that tells the sensor that these fatigue cracks are showing. These developed governing equations are used to develop the sensoring technology for stick and detect sensor nodes. And again, the skewness and modulus are going to be used for this algorithm to let the users know that there are fatigue cracks. There was actually 2 experiments done to verify that these stick and detect wireless sensor nodes are useful for our users. The laboratory scale validation was using aluminum plates. The sensor node tested was on 2 identical aluminum plates of 6061 T6 specimens. Each had a 15 millimeter fatigue crack that was propagated from the center hole shown in the figure on the right. The test was done with an Instron 8801 with a 10 Hz cycle rate and a max load of 25 kilonewtons with a stress ratio of 0.1 was applied to both of these aluminum plates. The identical experiment was repeated using conventional wired data. As shown from both the stick method and the conventional method, the HF and LF signals are set with a peak-to-peak voltage of 20 volts. These responses are measured with 1 megahertz sampling rate of 0.25 seconds, showing that these 2 methods worked identically. These are the results for experiment 1. Both the skewness and median values are negative for the intact specimen. Comparable results are made using the conventional wired systems, shown in the figure on the right. Hardware specifications of proposed sensor node and conventional wired systems are not the same. The ultrasonic modulation and noise values or corresponding threshold are not identical. The fatigue crack in the aluminum plate specimen is successfully detected by both hardware systems. As we can see on the graphs on the right, both the stick and detect method and the conventional method both predicted the stress cracks that were shown. This is experiment number 2. The wireless fatigue crack detection sensor to real situational structures is shown here. The Yingjiang-Graham bridge is used for fracture fatigue testing. The wireless stick and detect nodes were attached to the west end of the suspension bridge. They are attached near the welded connections on the upper deck where high stress levels are expected due to train passages. These areas are known for fatigue cracks based on prior inspections. These sensors need to be placed in these areas where these stress fatigues are susceptible to crack. The sensor data is then transmitted from the sensor node to the sync node. This is the results for experiment number 2. The 44 Ni values are tamed by fitting an exponential distribution to the 4 noise values. This was concluded that there is no fatigue cracks near the inspected location on the west side of the suspension bridge. Robustness of the proposed crack and detection was also checked. It was shown again that the skewness and the median values slightly vary from the test to test, these tests being the stick and detect method from the normal conventional method. The values obtained remain negative, indicating that there are no major cracks in the monitored location, saying that this suspension bridge is okay and has no fatigue cracks so far from the passing of trains. So for conclusion and concluding remarks, the stick and detect method for structural health monitoring and fatigue crack detection shows plausibility and how it actually is compatible to modern techniques for structural health monitoring. Both experiments have been implemented design of stick and detect method and have shown comparing results to other traditional methods of structural health monitoring. Nonlinear ultrasonic modulation techniques and free crack detection algorithms were developed in this case. This will ensure that the fatigue crack can be detected in earlier stages of life without relying on any history data of the target structure. Both tests have indicated a possibility for stick and detect methods to be potentially used in the future for fatigue crack detection. The performance of this sensor node is validated by comparing the fatigue crack detection results in aluminum plate with the results obtained from the conventional wired systems. This was also validated with the suspension bridge experiment held later on. What we can learn from this is that the stick and detect method sensors are going to be highly used in our future. With that, I want to say these are my references for this paper, and I want to say thank you for watching my presentation today, and I hope you all learned something valuable and important about the stick and detect method for structural health monitoring. Thank you all, and have a wonderful day.